Great. So as Christine and Norm both said, over the summer, early this summer, a panel was convened to review a huge volume of simulation results produced by the broadband platform and try to develop a set of evaluation criteria with respect to PSA and in particular median PSA. Let's see, arrows, there we go. So the committee that was formed, where's the pointer? This one.
That's actually recording US. Should be
Oh, there it is. Very good. Right. So the panel that was convened include Greg Baroza from Stanford, Steve Day from San Diego State, myself acting as chair, Christine Goulet from UCB, Tom Jordan, USC, Paul Spudich from USGS, and John Stewart from UCLA. And as we just heard, there are at this point, five participating models. Two of the models involved a deterministic summation of Green's functions. So one is the composite source model developed by John Anderson. The other is the UCSB model developed by Ralph Archuleta. And then we had one purely stochastic method, XSIM. And so XSIM is the, I guess, the sibling of SMSIM, extending to a finite source representation. And then the last two models, GNP, Graves and Pitarka, and San Diego State, developed by Kim Olson, are referred to as hybrid approaches. And so that means that they also use a deterministic summation of Green's functions at lower frequencies, and then at higher frequencies, they utilize a stochastic model to better explain the higher frequency components. And what they have in common is the deterministic summation at the lower frequencies, but then they have different stochastic models. Okay, so the review process was quite involved. It began in June. In June 11th and 12th, we had a two-day workshop in which the modelers were preparing for a subsequent workshop that was held on June 26th, the formal review meeting. Some of the review committee did attend the June 11th and 12th meeting, and we had very fruitful, in-depth discussions of all of the methods. We learned quite a bit about the different approaches. On June 26th, the panel met, and each of the modelers presented their method, their self-evaluations, and then the panel asked questions of all of the modelers, trying to get a little bit more information about each of the approaches. Okay. So at our disposal, we had the simulation results provided by the broadband platform, Part A, which involved looking at spectral acceleration 5% damp for the 7 events that are directly compared to observations for a rock site condition. And we had goodness of fit plots, as Christine described, for single scenarios and averages that were provided by the broadband platform. So we had mean bias plots. These are simply the residual, the natural logarithm of the ground motion. We also had the distance dependence plots and the spatial dependence. Christine showed examples of that, and I'll very briefly show them again. We had goodness of fit values that are provided in terms of distance, period, and source type bins. One of the things that the panel recognized early on is that it's just a very large data set to try to get your head around. And when you're looking at those goodness of fit parameters, those bias plots, you visually can see whether methods are performing well, but we needed to break it down into more specific cases. So we broke it down into distance bins and also different period bins to try to get a little bit deeper understanding of how well the methods were fitting the data. We also developed additional metrics based on goodness of fit, in particular a distance metric. Part B was provided to the panel, and as described by Christine, plots were simulated for ground motions for MW 6.2, 6.6 strike slip and reverse slip cases. They considered both a Southern California and a Northern California velocity model. And what was provided to the panel was the acceptance thresholds, as Christine pointed out, is based on the 2008 NG West models, looking at the maximum excursions of all of the models and then applying it uniformly over a period, but also applying a 15% factor to that. So 1.15 of the maximum value, maximum minimum value of all of the GMPEs. So these are the plots that are produced. This is for a single simulation. This is the simulation seed. Distance is less than 85 kilometers. Ground motions were simulated for the north-south component, east-west component. Rope D50 was computed. Red is showing the mean. Yellow is the 90% confidence of the mean. And was that teal? It's different on my screen. I think this projector's on the way out. The standard deviation. And so this is for one simulation. And then we have 50 realizations. And this is an example for the SDSU method. And so what we're looking at is a function of period, 0.01 seconds to 10 seconds period. And what we're looking for are mean values that plot as close to the horizontal line 0, indicating no bias. So you can see that it'd be very difficult to just look at large numbers of these plots and assess directly performance of methods. So we tried to break it down a little bit. We also had, and this is an important point that Christine made, was the bias plots for the GMPEs that were used. And so we developed a measure in which we could normalize the Part A validation values with respect to the GMPEs. And this provides an event term correction. So these are examples of distance plots. This is a linear distance plot. Again, it's increasing distance 0 to, say, about 100 kilometers there. This is the natural logarithm of the ratio of the observed to simulated values. We look for values that are as close as possible to 0. If values are plotting below the line, that's indicating that the simulations are over-predicting the motion. And each one of these panels is for a different period. So that's for 0.01 seconds, and it's hard to see, but that's 1 second there, 3 seconds there. And we also had these map view plots that helped identify directivity effects, but then also it helped identify cases where maybe there's a departure from the assumed one-dimensional velocity structure. At this stage in the broadband platform, all of the methods are using a one-dimensional velocity model. And some of the methods have capability for 3D models, but that's the scope of the effort at this point in time. Okay, so the Part B validation was the essentially the GMPEs, spectral acceleration here is a function of increasing period. And I won't go through all the nitty-gritty details again, but the point is that the black curve is showing the median of 4 NGA West models, 2008 models, and then the maximum excursion from these models, maximum and minimum, multiplied by 1.15 was then applied uniformly to all periods. That's what's shown as the dash curve. And so the acceptance criteria is that the median simulated motion has to lie within those dashed lines. It's a little bit less than a factor of 3. The distance here is more than a factor of 2. Turns out it's pretty close to one of the threshold values that we used for our Part A validation that I'll be describing. So when we come back to Part A, we're looking at direct comparison of observed and simulated spectral acceleration for the specific events listed here. And we're looking at comparisons of mean bias, okay, so the residual, the natural log of the simulated ground motion to the observed. So we had to come up with 2 thresholds. We felt that a failure threshold was reasonably a factor of 2. So the simulation method should at least be able to explain observed ground motions to a factor of 2. Natural log space, factor of 2 is 0.69. So if the mean bias was larger than 0.69, then that would constitute a failure for that particular case. Thresholds of 0.5 and 0.35 are considered as passing criteria. Here it's a little bit, we have a choice on what to take. There's some meaning to the 0.35 at long periods. So at long periods, 0.35 corresponds to a tenth of a magnitude unit uncertainty. Okay, so at long periods, we're saying that the ground motion simulation should be good to within a tenth of a magnitude unit uncertainty. Okay, so we also developed a method looking at distance dependence of the mean bias. And here we distilled the data down into a curve fitting exercise. This was suggested by John Stewart, in which we estimated the slope of the goodness of fit in discrete distance bins. And then we compared that to the 95% confidence of the slope estimate. And that proved to be very helpful. Okay, and then we also did comparison of mean bias and mean absolute bias with the GMPEs. So this is that last one is sort of grounding, taking into account event terms. So I realized that I fail PowerPoint presentation 101 because I have, not only do I have a table, but it's the most horrendous table you've ever seen. But this is the information that we had, and I'm about to argue that in fact it's not a table at all. The numbers are still on it, but you don't need to worry about the numbers. So the reason why we have this is just demonstrates how much information. I'd probably have 100 slides if I had to pare this down. But basically what this table or figure is showing is in the columns, in these wide columns, we're looking at the mean bias estimate between 0.01 to 1 second, 0.1 to 1 second, 1 to 3, and then more than 3 seconds. And that's for each of the methods. So here's CSM, UCSB, XSIM, GNP, SDSU. This column is actually the GMPEs that were used, and this is SSIM. So we had SSIM available just for reference, but we weren't evaluating that. So those are the columns. And the large rows then, this block here, that represents those observations within the 0 to 5 kilometer distance range. This is 5 to 20 kilometers, 20 to 70 kilometers, and 70 to 200 kilometers. And then in each one of these are the specific events. So you can get down to the event-specific performance. So for example, this is Northridge. Northridge at 0 to 5 kilometers. There's actually no information there. So here's Loma Prieta at 0 to 5 kilometers. Okay? In each one of these, we have the average also for California and the average for all. So splitting out the two Japanese events. So what's important to take from this table is the color coding, and that's what makes it a figure. So the color coding for this particular case is color coding red is indicating natural log value of 0.69. Okay, so that means the ground motions have deviated by more than a factor of 2. The acceptance criteria is 0.5 in this case. So what we find is that the methods perform quite well at relatively high frequencies, short periods, and in the passband, important passband from 0.1 to 1 second period, you start to see a little bit more red coming in at the longer periods. And we'll see maybe some better examples of that when we look at the GMPE comparisons. Okay, so that's one. And here, if we use a more stringent criteria of 0.35 natural log units, again amounting to plus or minus 0.1 moment magnitude units, then we see again that there is, for example, looking at the 0.1 to 1 second column, there are quite a few cases that are performing well within this acceptance criteria. What we see is we go to 1 to 3 seconds and more than 3 seconds, and there's more of the red cases coming into play. Okay. All right, so the other measure was when we looked at the raw distance data as Christine pointed out, you could see linear trends in some of those observations. And so the idea is that, well, we should at least be able to account for the distance attenuation. And so what we did was for each one of those bins, we can, for each scenario, we can have a bias estimate. Okay, so each one of these symbols is the bias estimate from that previous table in the respective distance bins. So we have 4 distance bins. And then we simply fit a line to those 4 bins and estimate the statistics on that. And in particular, we're looking at the 95% confidence of the slope estimate. So you can see that, for example, this case, the slope is 0. And here, this is a case where there's more of a slope. This is a case where you can see the slope is a little bit larger, outside the 95% confidence. So we made a more reasonable table based on this. And what I have here is the period range from 0.01 to 1 second, and the different period bins and the different methods. And so what we're looking at now is the ratio of the absolute value of the slope to the 95% confidence of that estimate. And so where ratios are less than 1, then the slope is contained within the 95% confidence. So effectively, there's the distance dependence of the simulation is matched. And so for these, we find the GMPEs perform well in this respect, and then 3 methods, XSIM, GNP, perform well. GNP for longer periods is getting a little bit close, but still less than 1. And these 2 methods have different cases where relatively large slopes were observed. Okay, so the next measure was to combine 2 different estimates. One of the things that we recognized was that if you just looked at mean bias, if you had a curve that, let's say, started off here and then it drift over some period range of interest, and it is uniformly distributed on, say, the positive side or the negative side of this, that we would have a mean bias of 0. But there would be clearly a misfit. And so what was done to handle that was to consider both the absolute value of the means weighted against the mean of the absolute value. So if we take the absolute value of the bias and then we average across that, and there's a significant trend in the bias plot, then we would be able to capture that information. So we equally weighted each of these. So that's one case. I'm about to show you one of those tables again. The other case was then once we had this combined measure, we also computed the same for the GMPEs and looked at that ratio. And so that's essentially correcting for possible event terms for each of those specific scenarios. Okay, so when we do this, we have the same general layout and really the more or less same results. It's a little bit worse. So this is for a threshold of 0.35. So there's specific cases here where maybe there's some slope to the bias plots. Okay, but we felt that the green and the white regions were relatively good. Again, red is not passing by this criteria. And this plot is showing the combined metric with respect to the GMPEs. And so what I've done is color-coded the columns for the GMPEs now, just to highlight them. And what we've done is we've taken this combined metric and we divided by the GMPEs. And so actually where it's green, the mean bias is less than the GMPE estimate. Okay, so there's some improvement here. And it's looking pretty good in the center of each one of these columns. Okay, so that's the Part A validation. Now, going to the Part B validation, what I'd like to show you next are 2 cases for the magnitude 6.2 strike slip case, one using the Southern California velocity model, the Northern California velocity model, and so we can look at those differences. So here now we have panels for CSM, UCSB, XSIM, GNP, San Diego State, and SSIM just for reference. Okay, so we have our acceptance criteria, which are the dash curves. And if I just toggle between the two, you can see the effect of velocity model. And just to point out again, for example, in the hybrid approaches, this is longer period up to about 1 hertz. That's going to be more or less controlled by the deterministic Green's functions. At periods less than that value, the various stochastic models come into play. But you can see that there is some slight variation, but for both of the velocity models, those 3 methods are within that criteria. If we look at CSM, for example, here you have curves that are within the acceptance criteria. Maybe a little bit, whoops, let's go back. Just touching outside here. You go to the Northern California model, it fits quite a bit better. If we look at this method, UCSB, that we see some structure in the shape of the GMPE that appears to be velocity model dependent. Okay, so another case I'd like to show is for magnitude 6.2 and 6.6 strike slip case, and then also the magnitude 6.6 reverse case. Yeah, so here we go from 6.2 to 6.6. Again, you can kind of get an idea for the stability of the approaches as you're changing magnitude. GMP in this case gets up towards the upper limits of the acceptance criteria, but is still acceptable. And we go to the reverse case. So you can see that there is some slight mechanism dependence, say for these 2 methods. For CSM, there's a fairly large mechanism dependence. Okay, so the last set of the Part B validation is comparing the moment magnitude 6.2 strike slip cases for distances of 20 and 50 kilometers. Distance performance. We'll make that same comparison for the 6.6 strike slip cases and 6.6 reverse slip cases. So here we have 6.2 at 20 kilometers, and we go to the 6.2 at 50. Okay, so the curves shift down systematically. We can see that there is some difference in the stability as a function of distance among the different models. And this is for the magnitude 6.6 case at 20 and 50. 50 looks a little bit better, perhaps. And the reverse faulting, 20, and again, 50. So those were the data that we had at our disposal. And I realized that in just 25 minutes or so, it's practically impossible to really, give you an in-depth analysis of this. But the panel did prepare a 30-page report that has 5 appendices. It was submitted on August 1st for review. And a general conclusion is that the broadband panel objective of version control and numerical test beds that Christine described is actually a huge success. I would argue that it's a huge success because by having all of the methods brought into the broadband platform with strict version control and third-party operation, and the uniformity in terms of the output products of the broadband platform, that was clearly a success because the output was such that it enabled a review. So a big improvement over the previous efforts. All of the currently implemented methods should continue to be refined and improved to provide a variety of options for users and to capture the epistemic uncertainty. And as Christine pointed out, for our project, we are locked in at version 13.6. And so we're going to move forward with that, but the broadband panel is continuing to do an analysis, and there will be future versions and more methods available. At this point in time, based on median PSA, 3 methods, XSIM, GNP, and San Diego State were found to be suitable. From the 0.01 to 3 second period passband, and over the distance range from 0 to 200 kilometers, with the caveat of within the validation magnitude range, which is moment magnitude 5.9 to 7.2. The methods are deemed suitable up to magnitude 8 for purposes of assessing relative effects of changes in source geometry. So these are the sorts of things that Katie talked about earlier about having complex ruptures or splay faulting. So looking at relative effects, the methods seem suitable for that. Also looking at source geometry rupture direction, hanging wall effects. But additional work is needed for absolute amplitudes. And at periods longer than 1 second, there is an increased bias. And I realize now that I actually neglected to point that out. So why don't I skip back quick just to point that out. You can see it here in this plot. So if we look at GMPE, then we go to about 3 seconds period, a little bit longer than 1 second period, you can see that the values are noticeably higher than the GMPEs, and that's consistent for all of the simulations. Okay, so that's something to look at in the future. Right. So I'd be happy to take any questions now. What we're going to be doing is segueing into a discussion session with the modelers. Yes, Katie.
I got you.
So for the bias and the long periods, it looked like there was a difference between the Northern California model and the Southern California model, that perhaps there was a larger bias, maybe for the Northern, if I'm remembering it correctly.
The longer periods?
Yeah, am I imagining that, or is that real?
We did notice a difference, but we're really focusing on that period range where we're looking at. So the argument would be that the Northern California model seemed to do a little bit better with respect to the GMPEs. Now we thought about what might be producing that long period bias, and one possibility is that the one-dimensional models that are used are producing very strong surface waves. And it's possible that once we go to 3D models that will change. The other possibility, of course, is that it's real, and it's not something that's being captured because perhaps the limited bandwidth of empirical data. Tom.
Tom Heaton, the bias that you saw, was it have a distance dependence? I mean, when you get in close, certainly the models, in a sense, once you say what the slip is, they can't miss the long periods, right? I mean, it's...
You're talking about long periods close in.
Yes.
We see it long periods pretty much across the board. You know, it becomes more dramatic as, you know, so this is an example that can illustrate this. So for example, the North Palm Springs event pretty uniformly is producing a bias. This is for distances from 0 to 5 kilometers at greater than 3 seconds period. Loma Prieta too. But then when you go to larger distances, 5 to 20, 20 to 70, and so on, then we see a lot more red, so the bias is increasing. And so that's what leads to, you know, a hypothesis that perhaps overly strong surface waves might be contributing in the synthetics, in the simulations.
Yusuf Buzurg. Doug, you mentioned other methods can continue, refine their methods. Is it open-ended, or is there any deadline on this?
I think that's really a question for Christine. And
For SWUS, the clock has stopped ticking in June. For the other projects, the broadband actually released June 2013, and they actually released version 13.9 last week. And we're in G East, for example, we keep on, getting modifications. So this is going to go forever. Is the short of the answer.
Norm?
So we're back to you speculated that the issue with the over-prediction at long periods was from surface waves. Is that right?
Well, that's one possibility.
Does this go away when people are using 3D velocity structure, or do we not know that?
I don't think we know that yet. I think Arvin Parkin may be addressing that later
He's
on.
going to give us some talk. I'm not sure if he's gone through that detail or not, but this comes back to what should we be using out at these long periods where ideally you trust, we think that the theoretical models should be working, and that's really where they're missing. So do you guys have more of an explanation than
But
just...
they're missing with respect to GMPEs at periods very close to where
But you also did
there's
it
limited data.
when you compared it to data, right? It also missed.
This is the GMP table. Can you show the other table?
Which one would you like to see?
Combined metric, not the
Oh,
GMP. Yeah, the previous.
Yeah, right.
That one.
So these are longer than 3 seconds. That's all data, right?
That's with respect to data, yeah. So you can see that there are specific cases where, whoops. So there are specific cases. So for example, North Palm Springs stands out.
But it's
That's at close distances.
But there's
Surface
le-
waves are going to start to become important at, this distance range 5 to 20.
but there's
those
less
periods.
green at the right-hand part of your plot than there is in the middle, right?
That's right. But one difference is that the data that is being used was processed, and that the synthetics are just broadband. That's my understanding.
Yes, but we discarded the points that were beyond the processing. So this should be self-consistent, but
Yeah.
the thing that gets difficult to judge is the last wide column, is that you might have only 2 points in some cases to define this ratio. So it's hard, the uncertainty is there. We divided by the number of cases we weighted, but it's uncertain, but it's true that it's wider, starting at 1 second.
So at this point, your panel is recommending the models are usable up to 3 seconds. And you're not giving us a recommendation on what to do beyond 3 seconds. Is that
That's
right?
Yeah. That's what we have.
And we're going to have to make a decision beyond 3 seconds as well, right? And part of this, I guess, when we get to the modelers, is asking them themselves, do they advocate using the models with a 1D structure beyond 3 seconds?
I think that they pretty uniformly advocate for,
For
at least for
doing
the
so.
the 2 hybrid methods, they're advocating for 3D.
Up to 3 and not beyond 3?
Well, we could ask them that
Okay.
question.
One comment there is we're having this whole discussion through magnitude, and all these long period models really are slip models. They say
Right.
we've got some amount of slip on a fault, and especially in close, what are the sizes of the long period motion in close? And there's not much way to get that part wrong, actually. I mean, in fact, that's where a lot of the slip models came from, inverting the same kinds of methodologies to figure out what
No,
slip was. So,
That's right, but what we're doing, what we have here are random realizations, right?
well, and there may be some tricky part there, but at the end of the day, since we're going all through magnitude in these probabilistic things, it points to an inherent weakness, which is magnitude tends to remove information from the system. You can have lots of different kinds of slip profiles with the same magnitude.
Of course. Yeah.
And what you really want to know is the slip on the fault, but that takes more information, and we just, in this business, just say, well, it's a magnitude 6.3 or something like that. And that removes information from the system, and it's probably related to things you're seeing here.
So the effort is to, I mean, it's couched in terms of a moment magnitude, target moment magnitude. But there are 50 slip realizations to try to get that variability, to capture that.
So on Norm's question, this is John Stewart from UCLA. On Norm's question about the, is the reason that the bias at long period is that from surface waves or something else? And can we connect it to the one-dimensional structure that was used in these calculations? We did do some work on the shakeout simulation from a few years ago that ran it through a 3D velocity model. And we don't have data to compare it to, but if you just look at event terms from the NGA GMPEs of the data generated through that simulation, they do go very high in the same period range where we're seeing it go high in these 1D models. So while this is not definitive, there's no actual data to compare it to and things like that, it seems to me that there's going to a 3D representation is maybe not going to remove the problem. There may be more to it than that, based on what we're seeing. Now, this was in basically the Graves and Pitarka model, so it's only one method was looked at. So there may be more to it than just 1D, actually.
One more?
Christine Goulet, to follow that up. So I think we're back to the question, what are you going to do with long periods? And even if you go to 3D, which we started with Arben Pitarka on specific scenarios, there's so much uncertainty in the models themselves, and how many 3D models are you going to run to figure out which one works for you?
Right.
So I think that for the short term this project has, you have to find a simpler solution. That's my big piece of wisdom here. 3D is not going to resolve this short term, I think.
But Christine, John's comments were that 3D, even if you did it, isn't going to help you that much, right? So you may still have this overprediction or this difference. And then it would have to be coming from something from your source or your rupture generator doing that?
Well, it could be velocity model too, right? So I suppose if it's too costly to go 3D and not all the methods can accommodate 3D, then what could be done is to try and look at more one-dimensional models and see what sort of variability you get at those longer periods due to velocity structure, a simplified velocity structure.
One more point we didn't really address, and we thought we would at some point, but we didn't see big issues, is we corrected the data, and if there's a bias in the side factors, that's going to show everywhere, right? So that's a thing we thought we would look at some point, not just for long periods, but we used an empirical model that might not be well constrained at long periods, although it should be linear, fairly easy to predict. But if there's a bias in that, the bias might come from that and not from the simulations themselves.
Is there a plan to look into that? Is there
I don't
a
know.
way to
Is
assess that?
Is there a plan to look into that? I'm looking at
I
Norm.
think there needs to be, because
Yeah.
this is really, you're right, I mean, that could be a factor of 1.5 or more floating
Yeah.
around.
And actually, the thing I didn't mention is that we used also for the long periods, we used the Chu and Young's Bayesian effects on top of this model. And I kind of remove it, but when so I did multiple tests early on with different side factors, and you needed a big differences in side factors to effectively change those ratios. So, but I just want to make sure that it's something that could be contributing to this as well.
That's a good point.
I think we should, even if it ends up not making a big difference, we should update to
So
the,
Rob,
we should update to an NJ West 2 Bayesian model.
But Rob had a comment on the web. How does he talk? I think you can go ahead, Rob.
Okay, can you hear me?
Yes.
Okay, so this is Robert Graves. I think what's happening here, and this is kind of just based on my experience, is that it is a combination of factors that are contributing at the longer periods. I think 3D is maybe one potential factor, but I also suspect force characterization is well. I think what leads to large, long period ground motions, it's situations where things tend to add up coherently. So that's coherence in terms of the velocity structure and surface waves, or coherence in terms of the source radiation. Both of those effects can come into play. The ruptures that we're generating, at long periods, there is a fair amount of coherence in the models, and they do have fairly strong directivity effects. The other factor, and I don't know how important this is, but the other factor that I think we need to consider for the source, our current models are just simple, single plane fault, planar. And there's some heterogeneity in the actual structure, the surface of the fault, where it bends around and so forth. That's going to break down that coherence of radiation. And that possibly could be another factor that would, could affect long periods, could also affect shorter periods as well. But that's something that the current